everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first topic we're going to look at is fundamental particles, and we're going to appreciate that knowledge and understanding of atomic structure has evolved over time, and that protons, neutrons and electrons are subatomic particles, and we're also going to look at their relative charge and relative masses, and then how an atom consists of a nucleus containing protons and neutrons which are surrounded by electrons. We're then going to look at the topic of mass number and isotopes. So we're going to look at mass number and atomic number. So by the end, we should be able to determine the number of fundamental particles in atoms and ions using mass number, atomic number, and charge, and explain the existence of isotopes. We're then going to look at the principles of a simple time-of-flight mass spectrometer limited to ionization, acceleration to give all ions constant kinetic energy, ion drift, ion detection, and data analysis. We're then going to look at how the mass spectrometer gives accurate information about relative isotopic mass, and also about the relative abundance of isotopes, and how it can identify elements and determine relative molecular mass. So by the end, we should be able to interpret simple mass spectra of elements and calculate relative atomic mass from isotopic abundance, which is limited to mononuclear ions. So now we're going to look at the evolution of atomic structure. So we need to know that knowledge and understanding of atomic structure has evolved over time. So firstly, we have Dalton's model, and he said that all matter is made up of tiny particles, which we call atoms. And he suggested that an atom was a tiny solid ball. And in his model, he said that atoms couldn't be broken down into anything simpler. So, cannot be And he also thought that all atoms of the same element were all identical to each other. And after Dalton's model was made, scientists used this model to make predictions. But sometimes the results of their experiments were a surprise, and they didn't fit with this existing model, so this model made by Dalton. And so scientists had to change this model slightly to explain any new evidence that they found. So first we have Thomson's plum pudding model, and this was the first development of Dalton's model. And the evidence which drove this model was the discovery of electrons. And we can write electrons as e to the minus because electrons are always negatively charged. And Thomson's plum pudding model was based on the fact that an atom was made up of tiny negatively charged electrons, which are dotted about a positively charged sphere, which is like a plum pudding. So when we have plum puddings, we have the cake, and then all of the plums are scattered about randomly within this sphere. So we have negative charges, we have negative electrons, dotted about a positive sphere. And Thomson also said that we could break atoms down into smaller parts. And the next development of the atomic model is Rutherford's model. And he found that if he fired some positively charged particles at gold foil, they bounced back when they were expected to pass straight through. And so he concluded that there must be a central positive nucleus where most of the mass of the atom is found. So we had firing of positive charges bounced back from an atom. So we had lots and lots of atoms in the gold foil, and when he fired these positive charges, he expected them to go straight through, but they actually bounced back. And so he made the conclusion that we must have a central positive nucleus. Where most of the mass is. And then we have Bohr's model of the atom, and this is much closer to the current model that we have now. And what Bohr found was that in-depth work on Rutherford's model showed that it had limitations and that the electrons should just spiral in towards the positive nucleus. And so he concluded that electrons move in fixed orbits. And this is around the central nucleus. And then after Bohr, scientists then discovered that the nucleus was made up of two types of subatomic particles. So we had protons and neutrons. And as a result of these discoveries, we now know that atoms can be broken down into smaller particles, so protons, neutrons, and electrons. Atoms of an element have identical numbers of protons and electrons, but can have different numbers of neutrons. And atoms of different elements have different numbers of protons and electrons. So they found that nucleus is made up of protons, which are positively charged, and neutrons. And these atoms can be split up into smaller particles, and we call these subatomic particles, and they're protons, neutrons, and electrons. We also have that atoms of an element can have a different number of neutrons but they have to have the same number of protons and electrons. But atoms of different elements can have different numbers of protons and electrons. Now we're going to look a bit more into subatomic particles. So atoms are made up of three fundamental subatomic particles. And so we have protons, neutrons, and also electrons. And the protons and neutrons we've seen make up the nucleus, so make up the central part of the atom. And they are held together by a force called the strong nuclear force. And this is much stronger than the electrostatic forces of attraction that hold electrons and protons together in the atom, and so it overcomes the repulsion between the protons in the nucleus. And so that's how this strong nuclear force can hold all the protons together, because normally they would repel each other because they have the same charge. And another thing to know about the strong nuclear force is that it acts only over very short distances, so only within the nucleus. And then what we need to know about electrons is that they surround this nucleus, and they're found in a series of levels, which we call orbitals or shells, and these get further and further away from the nucleus. And so looking at this example of a helium atom, here we have a proton, so it's a positively charged subatomic particle which is found in the nucleus. And then this green one here is a neutron because it's also found in the nucleus, but it doesn't have a charge. And the yellow one is our electron. Because it's in a shell or an orbital around this nucleus. And so now we also need to look at all the relative charges and masses. So we need to know their relative charges and also their relative masses. And so here we have the subatomic particle. And so first looking at a proton, its relative charge is +1 and its relative mass is 1. And then we have a neutron, and its relative charge is 0 and relative mass is also 1. And then we have an electron, which has a relative charge of -1 and then a relative mass which is much smaller than a proton and a neutron. It actually comes out to be 1 over about 1,840, so a lot smaller than the proton and the neutron. So you need to make sure that you know all of these relative charges and masses. Now we're going to have a look at mass number, atomic number, and isotopes. So these are three definitions that you really need to know. And the first is the atomic number. And we sometimes write this as Z. And this is just equal to the number of protons in the nucleus. And so the number of electrons in the atom is equal to the proton number. The proton number is also the atomic number. And so atoms are electrically neutral because we have the same number of positive charges and negative charges. And the number of electrons in the outer shell of an atom determines the chemical properties of an element and also what sort of element it is. And the atomic number defines the chemical identity of an element. And one really important thing to know is that all atoms of the same element have the same atomic number. So also because the number of electrons in the atom is equal to the proton number, when we look at the proton number, that means that we can see also that the number of electrons is the same. And then the second definition that we need to know is the mass number, and we sometimes call this A, and this is equal to the total number of nucleons. So what we do is we add up the total number of protons and the total number of neutrons, which are both in the nucleus, together. And it's the nucleons that are responsible for almost all of the mass of an atom because electrons weigh virtually nothing. So we saw that the relative masses of protons and neutrons were 1 and electrons were 1 over 1,840, which is significantly smaller. And then the last definition we'll need to know is the definition of an isotope, and that's an atom of an element which has the same number of protons but a different number of neutrons. So because it has the same number of protons, it also has the same number of electrons. And different isotopes of the same element react chemically in exactly the same way. And this is because they have the same electron configuration, because they have the same number of electrons. And atoms of different isotopes of the same element vary in mass number because we have that mass number is equal to the total number of nucleons, so protons plus neutrons. And because they have a different number of neutrons, all isotopes' mass numbers will be different. So for example, if we looked at a general element, so if we called this general element X, and what we would have would be, we would have A at the top and then Z at the bottom. So X is the element, and then we have A as the mass number, and then Z here as the atomic or the proton number. So this is how they're set out in periodic tables. So for example, if we actually looked at one of the elements in the periodic table, so for example, we looked at oxygen, and oxygen has a mass number of 16, and then an atomic number of 8. So now we can work out how many protons, neutrons, and electrons we have in this oxygen atom. So we know that the atomic number is equal to the number of protons. So for protons, this is equal to Z, which is equal to 8. And then for electrons, this is also equal to Z because the number of electrons is equal to the number of protons. And so this is also equal to 8. And then for the number of neutrons, we need to use the fact that the mass number is the total number of nucleons. So adding protons and neutrons together. And so that means the number of neutrons must be the mass number, which is A, and then minus Z. So it must be 16 minus 8, which is equal to 8. So we must have 8 of each of these subatomic particles in an atom of oxygen. And we'll also need to look at some ions. So for example, taking this oxygen, if we had an O2 minus ion, so oxygen likes to gain 2 electrons to form an O2 minus ion. And so for example, if we had O2 minus, and we still had this mass number 16 and the atomic number as 8, because these don't change when we add electrons. And so what we have is that protons stay the same. So we still have protons equal to the atomic number, which is equal to 8. But now the electrons, because they were the same as the number of protons, but now we have a negative 2 charge. So we have 2 more negative charges. That means we have 2 more electrons. So now it must be 8 plus 2. So now we have 10 electrons. And then the number of neutrons will also stay the same because we haven't altered the mass number in any way because electrons don't affect the mass number. And so we still have the mass number minus the atomic number, which still gives us 8 neutrons. So now we're going to look at time of flight. So mass spectrometry is a very powerful instrumental technique. And we can use this to find the abundance, which just means how much we have, and also the mass of each isotope in an element. And this allows us to determine its relative atomic mass. Because the relative atomic mass is just the weighted mean mass of the element in relation to 1/12 of the mass of an atom of carbon-12. And we can also find the relative molecular mass of substances made of molecules. So a common form of mass spectrometry is this time of flight mass spectrometry, and we normally shorten this to TOF. And I'm going to quickly talk through all of the stages we have in the process. So at the bottom, we have a diagram of a time of flight mass spectrometer. And firstly, we have the ionization area. So this is basically where we turn the sample into ions. So the first thing that can happen is electron impact. And electron impact is the process which happens to elements or compounds with a low MR. So the MR is the relative molecular mass. And what happens is that high energy electrons are fired from electron guns at the sample, and this knocks off an electron from each of the atoms in the sample, and so we form lots and lots of 1+ ions. And so what we have is an atom from a sample, which is going to be gaseous because our sample is gaseous. And then what happens is that we knock off an electron. So we get X+, so it's got 1+ charge, and it's still gaseous, but now we've lost an electron. If the sample is a high mol compound, we have something called electrospray ionization instead. So this is for high mol compounds. So basically compounds which are a lot bigger. So for example, we could have proteins. And what happens is that the sample is dissolved in a volatile solvent, so something that will evaporate really easily, and it's injected through a fine hypodermic needle as a fine spray into the vacuum. And this is into the ionization area. And a very high positive voltage is applied to the end of the needle where the spray emerges. And so the needle is positively charged. And this means that each particle will gain a proton and they will become ions as a fine mist. So we have that an atom in the sample, which is gaseous, will obtain a proton from the needle because the needle is positively charged. And so we'll form an XH+ ion. And this will have a 1+ charge, like what we had for electron impact. And then because the solvent is volatile, it will evaporate, and so it'll leave us with gaseous 1+ ions. And so the main point of this ionization area is to form 1+ ions. So electron impact is where we knock off an electron, and electrospray ionization is where we add a proton. And so from both of these methods, we can form 1+ ions. And then the second area we have is this acceleration area. And this is where all of these ions, these 1+ ions which have been formed, are accelerated so that they have the same kinetic energy. And they're accelerated using a negative plate because they'll all be positively charged, and so they'll be attracted to a negative plate. And we have an equation for the kinetic energy, and it's Ke is equal to half mv squared. So kinetic energy is measured in joules, and then m is the mass, and this is measured in kilograms, and v is the speed of the ion, and this is measured in meters per second. And then we have the third area, and this is what we call the flight tube. And this is where we separate the ions. So what happens is that the ions enter the flight tube, and this is called ion drift. And depending on their mass, they move at different speeds. And so the time it takes for them to reach the ion detector varies. And we have the general rule that ions with a smaller mass will have a smaller, what we call time of flight. So the time of flight is just how long it takes for this ion to get to the ion detector. And then finally, we have our detector. So this detector is a negatively charged plate. And a current is produced when ions hit this plate. Because an electron gets transferred from the plate to the ion because the ions are all positively charged. And so what we can form from this detector is what we call a mass spectrum. And this shows the number of particles or the abundance of each mass that hits the detector. So what we have is a mass spectrum, which we're going to look a bit further into a little bit later. But it'll look like this. So we'll have the abundance on the y-axis. So this is how much we have of each mass. And then what we have on the x-axis is something which we call the MZ ratio. And this is actually the mass to charge ratio. But if we say that all of the ions which are formed are 1 plus ions, then this MZ ratio will actually just... And one thing to note is that because current is produced when ions hit the plate, we have the relationship that ions or number of ions is directly proportional to the amount of current produced. And to see why ions with a smaller mass will have a smaller time of flight, we can use two equations to help us. And so the first equation we have is the one for kinetic energy. So we have that the kinetic energy is equal to half multiplied by m multiplied by v squared. And the second equation we can use is the one which relates speed to distance and time. So we have that speed is equal to distance over time. So if I rearrange this equation, we can find the time. So time is equal to the distance over the speed. And now we can work with the first equation and substitute this into the second equation. And so rearranging the first equation to make v the subject, we firstly have ke divided by half, so that'll be 2ke. And then we have to divide it by m, and then we have to square root it because the v is squared. And so this is our equation for v. So now we have equation 1 and equation 2. If we substitute, so basically put in our expression for v into the second equation. So we substitute 1 into 2. What we get is t is equal to d over the square root of 2ke over m. And this is equal to d multiplied by the square root of m over 2ke. Because we have to flip round. And now thinking about the kinetic energy, we know that all of the ions will have the same kinetic energy because in the acceleration area, we've accelerated all of them so that they have the same kinetic energy. And so this actually doesn't affect the time it takes for ions to reach the detector. And the distance here is the same for all of the ions because the flight tube is a specific length. And so these don't affect it. And so we have that t is actually directly proportional to root m. So this means that if we double m, t will increase by a factor of root 2. And so this is why we have that if an ion has a higher mass, then it'll take a longer time for it to reach the end of the tube. And therefore it has a longer time of flight. And now we're going to start to look at mass spectra which are produced from these spectrometers. So we produce mass spectra from a computer which is connected to the detector of a time-of-flight mass spectrometer. And a spectrum shows the mass-to-charge ratio, and we call this the MZ ratio, and the relative abundance of each ion, so the relative amount of each ion that reaches the detector. And the MZ is effectively the mass of each ion, because when we ionize these ions, we assume that we produce ions with a 1+ charge. And so we get mass spectra that looks like the one at the bottom. So we have relative abundance of the ions on the y-axis, and on the x-axis we have the MZ ratio. Now we're going to have a look at how we find relative atomic masses. So the mass spectrum of an element shows the mass and abundance of each isotope, and we can use it to work out the relative atomic mass. And this is just the average mass of the atoms. And we're going to look at the full definition of this a bit later, but we're just trying to work out the relative atomic mass using mass spectra. So the relative atomic mass is always given to 2 decimal places, and we can work it out by dividing the total mass of all atoms by the total number of atoms. So for example, find the relative atomic mass of neon using its mass spectrum. So we have that the average mass of atoms, which is equal to the relative atomic mass, which we label A with a little r. This is equal to the total mass of all the atoms divided by the total number of atoms. So what we can do to find the total mass of atoms is that we can use mass equals moles times molar mass, but we can actually use the percentages instead of moles. And so what we can do is we can do 90.90, which is the percentage, and then we can multiply it by the molar mass. And we can see here that this is the molar mass, and so we multiply this one by 20. And then we add up all of these separate masses of these different isotopes. So then we have 0.26 times by 21, and then added with 8.80 multiplied by 22. And then this is all divided by the total number of atoms. So in this case, that would be 90.90 plus 0.26 plus 0. And so this gives us a relative atomic mass of 20.17. So you always have to remember to round it to 2 decimal places. But sometimes we'll just be given the abundance data, so the amounts of everything we have, instead of the spectrum to look at. So for example, find the relative atomic mass of gallium using this data. So again, we have that the AR is equal to the total mass of all the atoms divided by the total number of atoms. So again, we do the same thing. So we have 1 multiplied by 69 plus 0.66 multiplied by 71. And this is all over 1 plus 0.66, which gives us 69.80. So basically we're working out an average of what the atomic mass is. So we're basically weighting it up because we've got quite a lot of this 69 and not as much of 71. And so that's why the AR will be closer to 69 compared to 71. So now we need to look at isotopes. And ions with different isotopes actually produce different signals. So we need to know about bromine and chlorine. So bromine can exist as a bromine 79, so bromine with 79 as a mass number, and bromine 81. And so we know that isotopes have the same number of protons and electrons, but a different number of neutrons. And so the bromine 81 must have 2 extra neutrons. And there's actually an equal amount of bromine 79 and bromine 81. But when we look at chlorine, chlorine exists as chlorine 35 or chlorine 37. There's much more of chlorine 35. Out of all chlorine atoms, 75% of the chlorine atoms are actually chlorine 35, and 25% of chlorines are chlorine 37. And this explains why, in the periodic table, the mass number of chlorine is taken to be 35.5, because we have so much more of these chlorine 35s, and so the weighted average is closer to 35 than to 37. And if 2 or more bromine or chlorine atoms are present, then the spectra becomes more complicated. And on another note, in organic molecules, there's often a small peak at the MR+1, and this is due to organic molecules having loads of carbons and hydrogens. And so a small number of the molecules will contain carbon-13 or hydrogen-2 atoms, which are isotopes of carbon and hydrogen. So the example we're going to look at is the mass spectra of chlorine. And chlorine, we know, comes as a diatomic molecule, so it comes as 2 chlorine atoms. And so there are 4 ways in which we can arrange these atoms. So we could use 2 35s. So we could have a chlorine 35 bonded to a chlorine 35. So this could be a chlorine molecule. Or we could have a 35 and a 37. Or we could also swap this the other way around. So we could have 37 and 35. And we could also have 2 37s. And now we can work out the probabilities of finding all of these different arrangements. So for the first one, we would multiply 75% by 75%. And so converting those to fractions, I'm going to write 3/4 multiplied by another 3/4. And this equals 9/16. And then here we have 3/4 multiplied by 1/4, and this gives us 3/16. And then for this one, we have 1/4 multiplied by 3/4, and this is also equal to 3/16. And you can see that these two are actually exactly the same. And so we add these together, and so we have 6/16. And then we have, for the 2 37s, 1/4 multiplied by 1/4, which is equal to 1/16. So now we can see the ratio between all of these different pairings. So the ratio we have is 9/16 to 6/16 to 1/16. And then we can multiply everything by 16. So we get 9 to 6 to 1. So we get a lot more of 2 chlorine 35s being bonded together in a chlorine compared to 2 37s. And this makes sense because we've got so much more of chlorine 35s anyway, out of all chlorine atoms. And so that's why we get the ratio of 9 to 6 to 1 on the mass spectra. And we can also see that this first one is 2 chlorine 35s added together, because this MZ ratio here, which is technically just the mass of it, because the charge should be +1, because when we ionize it, we turn it into a +1 ion, is 70, and 35 plus 35 is 70. So this must be 2 of these chlorine ions, 2 of these chlorine atoms bonded together. And this is a positive ion because it's gone through the time of flight. And then for the second one, we have the mass being 72, and this means that we have a 35 and a 37, which also makes sense looking at our ratio. And then this last one is when we have 2 chlorine 37s bonded together. Because 37 plus 37 is 74. Now we're going to talk about how to find the relative molecular mass. So we can use mass spectra to find the MR of molecules, and the MR is the relative molecular mass. So for molecules that are ionized by electron impact, the signal with the greatest MZ value is from what we call the molecular ion, which is basically the parent ion. And so we call this peak the molecular ion peak. And this MZ value at the molecular ion peak is equal to its relative molecular mass. However, sometimes there might be other small peaks which are present around this molecular ion peak, and this will be due to different isotopes. First of all, let's look at the mass spectrum of propane. Propane has been produced using electron impact. And so firstly, we look at the peak with the greatest MZ value. And first of all, you might think it's this one at 45, this one. But we actually need the biggest peak with the greatest MZ value, because this one is actually just due to an atom of hydrogen 2 or carbon 13, which are isotopes of hydrogen and carbon. And so this here is actually the molecular ion peak. So with electron impact, you usually go to the peak with the highest mass to charge ratio and whichever one is tallest. So in this case, it wouldn't be the very, very last one. It would be the second last one because the last one is due to isotopes. And so this tells us that the relative molecular mass of propane is 44. And all of these peaks, which are below this MZ of 44, all of these ones here, these are due to the fragmentation of molecular ions. And then looking at the mass spectra of a protein, because it's a compound with a high MR, we use electron spray ionization. And so we get this peak at the MR plus 1. So we do the same thing as the electron impact first. We find the peak with the highest mass to charge ratio and also the biggest peak. So that would be this one here with 521.1. However, this is the peak for MH plus because we've just gone through electron spray ionization. And so we should take one away. And so we have that the MR is equal to 521.1 minus 1. And so this gives us 520.1. And this small peak here at 522.1, this is due to MH plus ions, which contain one atom of carbon-13 or hydrogen-2. And so that's why they have a mass to charge ratio of 1 higher than this 521.1. So now we're going to have a look at some questions. So for question 1, the table shows some data about fundamental particles in an atom. For part A, an atom of hydrogen can be represented as H. Use data from the table to calculate the mass of this hydrogen atom. So what we need to do is look at the periodic table and look at how many protons, neutrons, and electrons are in a hydrogen atom. So on the periodic table, you'll see we have hydrogen, and the mass number is 1.0, and the atomic number is 1. So from this, we can see that the number of protons is equal to the atomic number, which is 1. And therefore, we have that the number of electrons is the same because it's a neutral atom. And the mass number, which is this 1 here, is the total sum of all the protons and all the neutrons. And because this is equal to the atomic number, we don't have any neutrons in a hydrogen atom. And so we have that the mass of this hydrogen atom is equal to the sum of the masses of 1 proton and 1 electron. So we have 1.6725 times 10 to the 24 plus 0.0009 times 10 to the power of 24, and that equals 1.6734 times 10 to the power of 24 grams. And then for part B, which fundamental particle would not be deflected by an electric field? So now we have to think about all the relative charges of these subatomic particles, or these fundamental particles. So we have protons, which have a relative charge of +1. We have electrons, which have a relative charge of -1. And we have neutrons, which have a relative charge of 0. And so it must be a neutron because it doesn't have a charge, and so it won't be affected by an electric field. Before I move on to the second question, feel free to click off the video and try it for yourself first. So in order to detect the isotopes of tungsten using a mass spectrometer, a sample containing the isotopes must be vaporized and then ionized. So for part A, give 2 reasons why the sample must be ionized. So one explanation is that we need to accelerate all of the ions to have the same kinetic energy. So the first reason we have is the acceleration of ions. And the second reason is so that we can deflect or bend the ions so that the ion flow is straight to the detector. And then for B, state what can be adjusted in the mass spectrometer to enable ions formed by the different isotopes to be directed onto the detector. If we've got different isotopes, then we can adjust the electric field to accommodate for these different isotopes. So we can adjust the electric field so we can make it stronger or weaker. And then for C, state and explain the difference, if any, between the chemical properties of the isotopes of tungsten 82 and tungsten 86. So if we first have a look at tungsten 82, so 82 is its mass number, and in the periodic table, tungsten has an atomic number of 74. And then if we have a look at tungsten 86, this time the mass number is 86 and the proton number is exactly the same. And so for this 82, we have that the protons is equal to 74 and the neutrons are equal to 82 minus 74. And then the electrons are the same as the atomic number, so we have 74 of the electrons. Whereas when we look at the tungsten 86, we have that the protons are equal to 74, and then neutrons, this time we have 86 minus 74, and then the electrons, we also have 74. And the key thing is that the number of electrons are the same in both of these isotopes. And because of this, there is not a difference in chemical properties between these two isotopes. Now we're going to move on to some harder questions. So for question 1, if the time of flight of a chromium 54 plus ion is 1.486 times 10 to the minus 5 seconds, calculate the time of flight of a chromium 50 plus ion. So the key thing we need to remember is that all of the ions in the time of flight mass spectrometer are accelerated to the same to have the same kinetic energy, and that's what we need to use. We have that the kinetic energy is equal to half mv squared, and we also have that the speed is equal to distance over the time of flight. And so putting this together, I'm going to put this velocity into this kinetic energy equation, and so we get that the kinetic energy is equal to half multiplied by the mass multiplied by d over t squared. And this should be the same for both of these ions. So firstly, working with this chromium 54 plus ion, what we can do is work out its kinetic energy. So we have this is of the chromium 54 plus ion. So we have half multiplied by the mass, so that would be the 54, multiplied by d over t squared. So d is going to be the same for both of these ions. So I'm going to leave it as d, so it's going to be a constant. And the time we have is 1.486 times 10 to the minus 5 seconds. And this is all squared. And so what we get is 1.223 times 10 to the power of 11. And we also have d squared, and this is an energy, so it's measured in joules. And then the next step we do is use this kinetic energy to find the time of flight of a chromium 50 plus ion. So what we do is rearrange this kinetic energy equation. So we get the time as the subject. So what we have is that the time is equal, so I've used this equation here and rearranged it to get time is equal to 1 over the square root of 2 multiplied by the kinetic energy over md squared, or this can be written as the square root of md squared over 2 multiplied by the kinetic energy. And now we can plug in our kinetic energy to find the time of flight for this ion. But please make sure that you use the whole entire kinetic energy that you found and not this shortened down version. So we type it directly into the calculator from the first step. So what we get is the time of this chromium 50 plus ion is equal to the square root, and then because the kinetic energy we found has this d squared and we also have a d squared here, these can cancel, and so we'll just have m, which is 50, and then over 2 multiplied by this 1.223 times 10 to the 11. But of course you type your whole number into the calculator and not just this shortened version, this rounded version. And so this gives us 1.430 times 10 to the minus 5 seconds. And one way you can check whether this is in the right region is if you look at the time for the chromium 54 plus ion, because we had 1.486 times 10 to the minus 5. So this has to be bigger than the one for chromium 50 plus ion because it's a heavier ion, and we know that heavier ions will have a larger time of flight. So before I move on to the next question, feel free to click off the video and try it for yourself first. So bromine exists as a diatomic molecule, and there are two isotopes of bromine. We have bromine 79 and bromine 81, and they're of equal abundance. Sketch the time of flight mass spectrum of the element bromine and then the molecule of bromine. So firstly, for the elements, what we do is we have on the y-axis the abundance. So this is how much we have of each ion. And then along the bottom, we have the MZ ratio. So for the element, we have a peak at 79 and one at 81. And these are of equal abundance, we've been told. And so therefore we'll have a peak here and a peak here, which is going to be the same height. So this is going to be caused by this bromine 79, and here we have bromine 81. Whereas if we were going to look at the molecule, we've been told that it exists as a diatomic molecule, and that means we have two atoms of bromine in the molecule. So therefore, we'll have again the abundance on the y-axis and the MZ ratio on this x-axis, but this time we'll have to add them up. There are three ways of forming a bromine molecule from two bromine atoms. So we can have two 79s. Actually, this will be these will be ions, sorry, because they'll have gone through the time of flight, so they've both lost an electron each. And so this would be our first ion. Or secondly, we could have 79 and 81. Or we could have 81 and then a 79. Or lastly, we could have two 81s. So the probability we would have the 79s, two 79s or two 81s would be a half multiplied by a half. So they would both be a quarter. So the probability of this would be a quarter, and this one would also be a quarter. And then here we would have a quarter again and a quarter again. And so because these two here are actually the same thing, therefore we add these probabilities up. And so we get a quarter plus a quarter is equal to a half. And so the ratio we have is equal to a quarter to a half to a quarter. And this is actually equal to 1 to 2 to 1. And so now we can draw our time of flight mass spectrum. So what we have is the abundance and then the MZ ratio. And then we have a peak at 79 plus 79. And that is equal to 158. And then we'll have the second peak at 79 plus 81, which is equal to 160. And this will be double the length of this one. This is 160. And then finally we'll have a peak at 81 plus 81. And this is equal to 162. So this is the same height as the first one. And so here we have the peak from the 279s. And this is a positive ion. Then at the top we have a 79 and an 81. And then on the right we have two 81s. So the key things to remember that we get the MZ ratios from adding up their mass numbers, and we get the ratio from looking at the probabilities. So we knew that there's an equal abundance of both of these bromine atoms, the 79 and the 81. And so we found the probabilities by multiplying two halves together to get the probabilities for forming a bromine molecule from two 79 atoms or two 81 atoms. And then for 79 and 81, we had to add two of those together. And so we got the ratio of 1 to 2 to 1.